Hello, this is Concrete Path. Today's lecture is going to be designed for solving the problems of your stress transformation and Mohrs circle. So your problem one, that's you have a state of stress. You have a state of stress given, and from that you need to get principal plane, location, and the value of principal stresses. That's major and minor principal stresses. Major and minor principal stresses. Major and minor principal stresses. Minor principal stresses. So, but the state of stress is not one. So we have three loadings. We have provided you three different loadings. Loading A, B, and C, and from that you need to superimpose the effects. You need to do a superposition, then get an equivalent state of stress, get an equivalent state of stress, and then accordingly you can calculate using the standard equations of analytical method, so we can get the sigma 1 and theta p location. But the state of stresses are provided because of three loadings. We have three different states of stresses on different planes. Say you have plane P and Q on which a stress of 45 sigma x is acting. Only sigma x is acting 45 megapascal on plane P and Q. And we have one more state of stress because of loading 2 that's making an angle of. So the plane is making an angle of. We need to calculate what's the angle that plane makes with the vertical. So the state of stresses looks like this part. So we have here a loading, a state that stress value equals to minus 60 megapascal, that compressive megapascal. So and the line of action of this stress is making angle of 60 degrees with the horizontal. So this is 60 degrees. And third state of stress is that, so actually this state of stress is, say this acts on plane R and S. So your 60 megapascal acts on the plane S plane. So it acts on S plane. So we need to say then we transform it. Then so third state of stress is provided that you have same this element but in the opposite direction. So you have a upward, that we can say tensile stress of 30 megapascal on plane U, T, because to U. So let's call them U and T. So so we can say this is making angle of, this is also making an angle of 60 with the horizontal. So this is 60. Then we can say if we transform them into standard P and Q planes, then we can write them as in this fashion, that this is 45 acting on plane P and Q, plus this is also some tau, and this is some tau xy1. There is some sigma x1 and there is some sigma y1 on plane P and Q, plus there is some state of stress acting on plane P and Q with some tau xy2, sigma x2, and sigma y2, such that the overall value would contribute to a state of stress on that plane P and Q, such that overall value is sigma y, sigma x, and tau xy. Then I can directly get anything. I can get theta p, theta shear, I can get tau x, tau max, I can get sigma 1, sigma 2. So this is the procedure how this problem has to get solved. So for the first part, there is no worries. It is already transformed into the plane P and Q. We want to transform the overall these loadings. These are three different loadings. We want to transform it into standard case. Our standard case that we used for derivation was this plane P and Q. So we have to transform loading B and loading C into our into our state of stress, that's P and Q. So deform. So this is three different loadings. Because of three different loadings, we have different state of stress on different planes, different loadings. So we had 6 planes, that's P and Q, R and S, U and T. So let's talk about case B. Let's take case B first. We say this is our element, stress element. It is subjected to tense compressive 60 megapascal. So we can say your sigma 1 major principal stress is 0, and your minor principal stress is minus 60 megapascal, and tau max, we can say tau is 0. If the tau is 0, then we can say this is a principal plane, or we can say this is the principal stress, and the theta it makes with the horizontal, that is 60 degrees. So we need to say what's the angle it makes with the, we are worried about the theta p, that theta, what is the theta it makes with the vertical, theta with respect to vertical plane, or we can say with respect to plane P, that was vertical. So let's say this is the line of action of force, line of action of stress, and this is horizontal. So this is 60 degrees, and we want to find what is the theta it makes with the vertical. What is the theta it makes with the vertical? This, yeah, with the vertical. Let's say this part. Let's say this is vertical face. We want to say what is the theta it makes. The plane is this one. This is our plane, desired plane. This is our desired plane on which stress is acting. So the desired plane is somewhat in this fashion, that it is perpendicular to the line of action of force, that stress. So we can have this part. So we can say this is plane, desired plane, and this is our vertical plane. So this is our theta that we had to find. So we can say if this is 60, this is total 90, total is 90, that means this part, this is 30, and this is 90, this is 60. So overall value of this one would be, that 180 minus 60, that is 120. So this part is 60, and then after 30, then we have 60. So overall value of theta equals to 120 degrees with the vertical plane. So if we use the analytical method, we would say what is the sigma x dash? We can say sigma x dash at theta equals to 120 degrees. But the thing is, this derivation was performed when the plane was already known that this is plane P and this is plane Q. On that, some sigma x is acting, sigma y is acting, and some tau is also acting. So if we use this equation, we have unknowns of sigma x, sigma y, and tau xy. But we know that sigma x equals to sigma 2 equals to minus 60. That sigma x equals to sigma 2 equals to minus 60 at theta equals to 120 degrees, or theta p. We can say this is the principal location, theta p2 equals to 120 degrees. If we use this equation, then we can say, we also know that tan 2 theta p equals to tau xy by sigma x minus sigma y. And we also know that sigma 2 equals to sigma x dash equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta p plus tau xy sine 2 theta p. So in this part, can you get the value of sigma x plus sigma y? That's acting on plane P, but you have provided on plane R and S. This is plane R and S. You are provided that stress is 60 megapascal on plane S, and there is no stress on plane R. That means sigma 1 plus sigma 2 we can say that's equals to 60. And if we say what is the sigma x plus sigma y by the stress invariance concept, that's also equals to 60. That's also equals to 60. So we can write that this is 60 by 2 plus sigma x minus sigma y by 2. So we have three unknowns. That one is sigma x, sigma y, and tau xy. That's acting on this plane R and S, and that's acting on plane P and Q. That then from the transformation that on the plane R and S there is no stress sigma x, there is no sigma x, or there's no tau. But if we transform this, it can have some sigma and tau on plane P and Q. That's what we have to find. That we have unknowns of 3. So we have 3 unknowns, and we have 3 unknowns, and we have 3 equations. One equation is that sigma x plus sigma y equals to 60. This is one equation. One equation is that we have here also this unknown. We have 3 unknowns, but we have 3 equations. So if we substitute this sigma x minus sigma y by 2 equals to, so we can substitute this value here. Then we can get some value, some equation in the form of, then what should we write that sigma x dash? That we write as minus 60. So we write, which implies minus 60, and this was minus 60 also. Yeah, this was minus 60. Sigma 1 minus sigma 2 was minus 60. Minus 60 plus 0. So minus 60. Then we can write that minus 60 equals to minus 30 plus, in terms of sigma x minus sigma y by 2, we can write tau xy by tan 2 theta p. And you have cos 2 theta p, and then again cos tau xy sin 2 theta p. And if you substitute the values of tan, that theta p equals to 120 and 2 theta p equals to 240, and you get a value of shear stress tau xy equals to 15 root 3. 15 root 3 positive. Positive means the this direction of shear stress on different planes would be in this form. This is negative, that's positive. This is negative, this is positive, and this is positive, that's positive. This is positive, that's positive. So shear stress is positive tau xy equals to 15 root 3. And if you substitute now that in this equation, now you can get sigma x minus sigma y equals to some value. Sigma x minus sigma y equals to some value. Then. So yeah. So you have this value that 15 root 3, and we have this 2 also, and divided by tan 2 theta p. Yeah. And you can get the value sigma x minus sigma y, and you also know sigma x plus sigma y equals to minus 60. Then you can get sigma x equals to, and sigma y equals to, so your sigma x and sigma y would be coming out to be equals to, sigma x is minus 15, sigma y is minus 45 megapascal. So final state of stress because of loading 2 on plane P and Q can be transformed such that the stress sigma x and sigma y, sigma x is minus 15 and sigma y is minus 45, and your shear stress positive. So your shear stress of 15 root 3 megapascal. So we have transformed the loading B into plane P and Q. Now our next case is the case C, because of loading C. So we had to transform this state also. So let's say this is the action of stress, and we have the plane. This is transformed plane. We have to transform it to our reference plane, that's plane P and Q. So your T plane has to be transformed into plane P and Q, So we would say that the theta, it would be this one, theta, with respect to vertical. So let's say this is our plane, this is plane, this is our plane, and the plane and the line of action is making 60 with the horizontal. So this is the line of action of force, of stress. It's making angle of 60 with the horizontal. So this is 60 degrees. And that means this is 30 degrees. So the plane, this is horizontal. This is horizontal. And we want to say, what's the theta with the vertical. So let's say this is vertical. This is our plane. So this is our theta. I want to find this theta. So I would say this is 60, this is 30. That means 60 is this one. This is 60, and that means this is also 60. This is also 60. This is 30. This is 30. This is 30. This is 60. Yeah. So theta equals to 60 degrees. And if we see that from this diagram, that you have sigma 2 equals to 0 and sigma 1 equals to 30. That means major principal stress is tensile. Tensile we take as major. If we have two values of stresses, one is 3 and then one is 5, we can say sigma 1 is 5, sigma 2 is 3. And if the values are -3 and 0, we would say sigma 2 is -3 and sigma 1 is 0. Similarly, if you have 3, 0, I would say sigma 1 is 3, sigma 2 is 0. So we take tensile positive, and major is according to their tensile value. So we have sigma 2 equals to 0 and sigma 1 equals to 30. And I would say that plane T and S, they are principal planes. They are at an angle of 60 degrees with the vertical, such that they can give a principal stress value here. So I need to get some external load. I need to get some standard loading because of the stresses that had developed on the plane P and Q, that generate your state of stress that was somewhat in this fashion, that 30 megapascal. So I need to convert that T and U plane into standard P and Q plane, such that the stresses here are sigma x2, sigma y2, and tau xy2. Then I could say what is the tan 2 theta p? What is the tan 2 theta p? I would say that's 2 times tau xy by sigma x minus sigma y. Similarly, I would say on theta, I would say at the rate of theta p equals to 60 degrees, I have sigma x dash, that's equals to sigma 1, that is 30 megapascal. That equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta p plus tau xy sine 2 theta p. And I know that by the stress invariance concept, you have stress of only 30 acting. There is no sigma in this direction, so this is 0. So I would say sigma 1 plus sigma 2 equals to 30. That means sigma x plus sigma y is also 30. So I can write that 30 equals to 30 divided by 2 plus, and I have substituted sigma x minus sigma y by this value, that tau xy, and I would write cos 2 theta p by tan 2 theta p. And similarly, in the third term, we have also tau xy into sine 2 theta p. So I would write plus sine 2 theta p, and I substitute the value of theta equals to 60 degrees at the rate of theta p equals to 60 degrees, and I can get shear stress value, positive shear stress value of 7.5 root 3. Then accordingly, I would say what is the value of sigma x and sigma y. Sigma x comes out to be equals to 7.5 megapascal, and normal stress in y direction, I would say 22.5 megapascal. So final loading would be final stresses would be now. Initially the first state of stress was given. So the first state of stress would remain as it is, that this state of stress was 45, so this is 45. And similarly, you have one more state of stress, that is now now some sigma x, sigma y, and some shear stress. Then I would say, then I have in the third case I had also some shear stress, I had also some sigma y, and I have also some sigma x. Those values we have provided here, that sigma y equals to 22.5, this is 7.5, and shear stress of 7.5 root 3. And similarly in this one, I need to get this one also, that 45 megapascal tensile, this is compressive. In the case B, there is compressive stresses. Stresses are compressive in the case 2. This is 45, and this is sigma x is minus times 15, and shear stress is 15 root 3. So final configuration would be, so you have 45 plus, then we can write 45 minus 15 plus 7.5. Similarly, you can say upwards, 0 minus 45 plus 22.5. And similarly, shear stress value of 0 plus 15 root 3 plus 7.5 root 3. So this is a shear stress of 22.5 root 3, and a normal stress is sigma y. Sigma y comes out to be equals to minus 22.5, and a normal that sigma x in y, sigma normal stress in x direction, that's equals to 22.5, 37.5, 37.5. So this is our final state of stress on plane P and Q. Then now we can get the location of principal plane. And stresses, major principal stresses. So I would say major principal stress sigma 1 equals to sigma x plus sigma y by 2, sigma x plus sigma y by 2 plus that radius tau max, that radius value of sigma x minus sigma y, sigma x minus sigma y by 2 whole square plus tau xy whole square plus tau xy whole square. Then we can get sigma 1, and I would say sigma 1 comma sigma 2. So sigma 1 and sigma 2 values are minus 41.7 and 56.7. So this is our final stresses, and I can get also the location of principal plane, that's tan to theta b. Tan to theta b equals to 2 times tau xy by sigma x minus sigma y, and we get a theta b equals to 26.1 degrees, and we can say 1 plus, you add 90 degrees, you can get 116.205, or we can say 26.1. That means this one should be 116.1 degrees with respect to vertical plane P. So this was by analytical method. If you want to solve by Mohrs circle, then first part is okay for now. Then for the second case, I have to solve it using Mohrs circle. So theta is same, that you have theta. The theta is that in the case 2. So we got a theta p equals to 120 degrees. That means 2 theta equals to 240 degrees. Now I want to plot these on the Mohrs circle now. So we got theta p, we got that is equals to 120 degrees. Now I would say I would say, what's the value? How should we get those stresses? Sigma x, sigma x, sigma y, and tau xy. So for that, so we have this that on theta p, and we can say in this fashion. Then on some plane p, on some plane s, your theta was equals to 120 degrees with respect to vertical plane. So let's make the Mohrs circle. So this is our origin O, and I would say, what is the center value equals to sigma x plus sigma y by 2. That's also equals to stress by stress invariance concept, that is sigma 1 plus sigma 2 by 2. That is the sigma average, or that center of the Mohrs circle. So from the calculation, that's 60 minus 60 comma minus 60 by 2, that's minus 30. Or if we take the sign, that we can say center is negative, minus 30, that means on the opposite side. So we have minus 30 in this side. So let's say this is minus 30. This is center. Similarly, what's the radius? Radius. We have the radius equation, that sigma x. How can you get the radius? If you don't know the values of shear stress and normal stresses, how can you get the value of radius? But in the Mohrs circle, we know that sigma max, that sigma 2, or we can say major principal stress, minor principal stress, that is 45. That's minus 60. Do we know that that is minus 60? So if we say this is our minor principal stress, minus 60, and so finally we can say this is radius r, this part is radius r. So you draw a circle of radius, r. So we got some circle, and we can say sigma 1, that sigma 1 is equals to 0. If the sigma 1 is 0, then that means from the center to origin, that's minus 30. That means radius r equals to minus 60 minus of minus 30. That's radius is also minus 40. We can keep the sign as of now, that positive. Then finally we can say this is on the compressive side. We can get some radius of 40 megapascal. So that's also tau max. You can say that's also tau max, some value of 40. Now this is our plane. Which plane is this one? Can you tell which plane is this plane? Minus 60 plane. This plane is that minus 60 is acting on plane S, and zero stress is acting on plane R. So this plane is R plane, and this plane is S plane. And I need to get the location of the principal. I need to get the location of tau plane, that's sigma x and sigma y, and tau xy, that's plane P and Q. How can I get the location of P and Q? How can we get the location of P and Q? Yeah, the theta we know that's provided here. We know that theta with respect to vertical was equals to 120 degrees. That means from the vertical, you go anti-clockwise 120, and you will receive some plane S on which minor principal stress of minus 60 megapascal is acting. Can we say that? That means we can write here anti-clockwise 120 degrees from vertical plane to receive plane S, on which minor principal stress sigma 2 minus 60 megapascal is acting. So if we say on Mohrs circle, how much it should be the angle? So we would say from the plane S, this is our plane S, you have to go anti-clockwise 120 into 2, that's 240 degrees. So somewhere here, so this is somewhere here. That means the plane plane P would be somewhere here, plane P. So this is plane P, this is plane Q, sigma x, sigma y. So from plane P, you have to go somewhere, some angle of 240, 90, 80. That means somewhere here. You have to go somewhere here. From this vertical, you have to go somewhere here to receive that plane S. This is plane S. So you have anti-clockwise theta equals to 240 degrees. So this is known to us. And similarly, next plane P, and this would be plane Q. This would be at angle of 180 degrees from plane P. So I would say, can we get this value theta? And this is also same here, theta, by the symmetry. This is theta, this is theta. If I am able to calculate, that from this triangle, if I have this triangle, that let's say this value, that is sigma dash. This is sigma dash. But the stresses acting on plane P, this is sigma x, because on plane P your sigma x is acting, that's sigma x. And on plane Q, this is sigma y. This is sigma y. So once if I am able to get the value of sigma dash, I would say that sigma x equals to, that center minus sigma dash. Center, I would say sigma x equals to center minus sigma dash. And similarly, I would say sigma y equals to center plus, by the symmetry, this is also sigma dash. Center plus sigma dash. Center plus sigma dash. So I need to get the value of sigma dash. This is the theta, that is 60 degrees. And I know that this is tau, this is radius, tau max. This is radius, this is some shear stress tau. So there is some shear stress tau. So here we can see that on plane P, you have some based from the Mohrs circle you have drawn. You can say on plane P your tau xy is negative, your shear stress is negative, that means anti-clockwise. So shear stress is negative on this plane P, and tensile stress of sigma x, that compressive stress of sigma x. So your coordinates would be minus sigma x comma minus tau xy. So minus tau xy. That's why on the plane P we can have sigma x negative and tau xy also negative. And for the plane Q, we have this plane Q. On which some stress sigma y is compressive, negative, and there is some positive shear stress. That means the direction would be in this fashion, tau xy, clockwise rotation of the stress element, or of that plane Q. So now we need to get from this triangle the values of sigma dash and tau xy. So this is radius, or the radius was equals to, let's take the positive values for now. The radius was 40 degrees. I would say 30. The radius was 30. Let's take radius as 30. This is sigma dash. Or if it's up to you, let's take the sigma radius equals to minus 30 as we get from this equation. Minus 30. Radius minus 30. Sigma dash, and this one is tau xy. This is 60 degrees. I would say sine theta, sine 60. This is tau xy by r. And that means your shear stress on that particular plane P and Q, because of some general state of stress, on plane S and T, S and R, you got some state that tau xy equals to minus 30 into root 3 by 2. That's minus 22.5 root 3. Minus 22.5 root 3. Minus 22.5 root 3. This negative here means that this triangle was from this plane. I would say this negative means the shear stress would be on this plane in this direction. Shear stress would be in this plane in this direction. That's anti-clockwise. That's why negative. I kept it here. I kept it here negative. So we got this value. We got this value. Let's take the that for magnitude now. Let's take the magnitude only. Then we can directly say what's the value that if you have this triangle, if you have the triangle, you don't say negative side is there. You would say some value of side is magnitude is there when you calculate the sides. Let's take the positive side values for now. Let's say this is positive value 30. So you got some shear stress 22.5 root 3. You got some shear stress value 22.3, but we know that on plane P and Q, your shear stress was downwards. On plane P, shear stress was negative. Shear stress was negative. That means the direction of shear stress should be in this fashion, that it's anti-clockwise. It's anti-clockwise. And similarly, for this plane, it was clockwise. That means the overall configuration of the shear stress would be in this fashion. That's positive shear stress. Positive shear stress tau xy. So this is positive. The possible Mohrs circle we got that shows that on plane P your shear stress is negative, and on this plane shear stress is positive. So this is only possible. So in this plane it has to be in this direction, and in this plane it has to be clockwise. Clockwise, it is anti-clockwise. So final stress would be a clockwise shear stress based on the stress representation and sign convention that we have studied in chapter 1. Overall shear stress is positive. So we got a value that 22.5 root 3, that's positive shear stress value. And if I want to say what's that value of sigma dash, I would say that equals to tau xy cos 60. So we got some value. Shear stress was 30, that means 15 megapascal. So 15 is sigma dash. Now if I say what's the value of sigma x, I said that sigma x is c minus sigma dash, and sigma y is c plus sigma dash. Your center was value of center was 30. Value of center was 30. So I would say 30 minus of 15, and sigma y is equals to 30 plus 15. That's 15, and this is also 15. But overall value would be negative 15, negative 45, because you can see from the Mohrs circle all the values of stresses are compressive. No stress is tensile. Each of the stress is that negative, compressive. Normal stress is all compressive. This was for the case 1, and if you say for the case 2, you had some stress element on plane UNT. You had some state of stress on plane UNT. Here we can say here sigma 1 is equals to 30 megapascal, sigma 2 equals to 0. That means center equals to sigma 1 comma sigma 1 plus sigma 2 by 2. That is 30 by 2. That's 15. And radius, that we can say sigma 1 minus center. We know that sigma 1 is c plus r. So we can say radius equals to sigma 1 minus center. Then we can say that equals to 30 minus 15. That's 15. So we got radius positive and center also positive. That means on this other side. So you have some center of 15 and major principal stress of 30. That means this is radius, and you draw a circle. So this is our Mohrs circle. So that sigma 2 is 0. So now the location that we have from the vertical, this plane T, so this is plane T, it's making an angle of 60 degrees. So I had to reach to the plane on which major principal stress is acting, So this is our principal location. That means you have to go anti-clockwise 120 degrees to receive plane. So this plane is plane T, and this plane is plane U. So you have to receive some plane T at an angle of 120 degrees from plane P. So there is some plane P. This is 120 degrees. So this is some plane P. Similarly, I would say this is the center, So your plane Q would be here somewhere. So this is our 120 degrees. So if this is 120, this is 60, then I would say this is 60, this is also 60. And now from this triangle, I can say, from this triangle, let's say this is sigma dash, this is tau xy, this is 60, this is radius equals to, radius was equals to 15, radius was equals to 15 radius. So we got a radius of 15, and I would say what's the value of tau xy? Tau xy equals to 15 sine theta, and sigma dash equals to 15 cos theta. Then I can get values of, this is 7.5 and this is 7.5 root 3. Now what is the shear stress? Is it negative or positive shear stress? See, I want to say what is the value of shear stress on the plane P. You have a on plane P you have a shear stress value of, that's normal stress value of sigma x positive, because it's on the tensile side, positive side, and similarly you have negative shear stress. That's only possible if on the plane P there is some anti-clockwise shear stress, and there is some positive tensile sigma x. So this is our that conclusion from the Mohrs circle that we draw. I would say shear stress is negative. That shear stress is acting anti-clockwise on this plane. There are two different sign conventions. One is that negative tau xy here on the Mohrs circle means the direction on this plane of the shear stress is anti-clockwise. And next sign convention for the shear stress, real shear stress, is that if the shear stress is such that we have this configuration, I would say the shear stress is positive. So there is a difference. So this part is anti-clockwise. This is anti-clockwise. That is negative in Mohrs circle, and this part, this is clockwise. This is positive in Mohrs circle because it is clockwise. But overall, shear stress is positive for the stress representation case. Now we got from the triangle that shear stress is 7.5 root 3 and sigma dash equals to 7.5. But center, we know center equals to 15. Center, we know that center is equals to 15. That I would say what's the value of sigma x. So this is center, and this is on the plane P, this is sigma x, and this is sigma dash. From that, this is sigma dash, and this is also sigma dash. Up to the plane Q, there is some sigma y. This is some sigma y. Sigma y equals to c plus sigma dash. So that c plus sigma dash, that is 22.5 positive. Similarly, I would say sigma x equals to c minus sigma dash. That's 15 minus 7.5. That's 7.5. So finally, you got three state of stresses, and you have to combine them to get the final configuration such that this is plane P, PQ, 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 and finally you have also PQ, P, and this is plane Q and plane P and Q. Then you can plot final Mohrs circle also. So based on this, let's plot final Mohrs circle. So this is our reference line. This is origin. Say your sigma x is minus 22.5. Minus 22.5 means it should be on negative side, and shear stress value is clockwise. So shear stress is clockwise. That means somewhere here, plane Q minus 22.5, comma shear stress value of 22.5 root 3. That value is equals to 22.5 root 3. That is 38.97. So you have this shear stress value and normal stress value on plane Q. Similarly, you have sigma x 37.5 and shear stress that is anti-clockwise. So negative shear stress, I would say. So shear stress would be somewhere here, and a value of 37.5, comma 38.97. Then you plot them, then you combine them, then you join them. Let's say this is our joining line. So this point where it cuts, I would say this is center. The value of center would be sigma x plus sigma y by 2. That is 22. That's 37.5 plus minus 22.5 divided by 2, and that value equals to 7.5. So this is 7.5, and the radius, I would say radius equals to, from the equation, sigma x minus sigma y by 2 whole square plus tau xy whole square root, and radius equals to radius value let's say some radius value would be there, and you join. This is our radius value, I would say. This is the radius value. So you join. There is some circle formed. So we got the shear stress. And then I would say this is sigma 1. I know that sigma 1. I don't know the value of sigma 1, but I know that the location of sigma 1 be at tan 2 theta p equals to 2 tau xy. The value of tau xy is 38.97. 2 tau xy by sigma x minus sigma y. So I could finally say what is the value of theta p, location of principal stress. That's 26.1 degrees. That means 56.2 degrees. That means this 2 theta p is equals to 56.2 degrees. And similarly, this would be 180 plus 56.2 degrees. That is 236.2 degrees. 236.2 degrees. 236.4 degrees. 236.2 degrees. So we got this one also. Now we have one more problem that we have plane stress condition given. Plane stress condition that you have a sigma x equals to 56 megapascal, and you have shear stress that's anti-clockwise. I would say that's negative shear stress, tau xy. Shear stress. The shear stress is said that it is anti-clockwise shear stress of tau xy. And I need to get this tau xy at the rate of, if maximum normal stress equals to 70 megapascal. So I need to get this tau xy if the maximum normal stress is 70 megapascal. So I would say if the maximum normal stress is 70, that means it's a major principal stress, because major principal stress is that all those stresses would be lesser than sigma all normal stresses, because all normal stresses would be lesser than major principal stresses. So your major principal stress of 70 megapascal, sigma 1, and there is some plane, and there is some plane P, on which some sigma is acting positive, sigma 56, and shear stress anti-clockwise, shear stress clockwise, that's positive shear stress 56 gamma tau. And on the sigma y, we say that sigma y is 0, because no stress is acting on plane Q. So I would say sigma y is 0. So 56 gamma tau you have to plot. 56 gamma tau, plane P, 56 gamma tau. So plane P, this is somewhere here. 56 gamma tau. Let's say this is 56 gamma tau. And plane Q would be at angle of 180 from this one, such that the normal stress value equals to 0. Such that the normal stress is 0. So we have plane Q, on which there's no sigma, I would say sigma 0 comma, and shear stress is anti-clockwise. So minus tau, 0 comma minus tau. So this point plane Q 0 comma minus tau. Now the radius, we can say radius, and center equals to sigma x plus sigma y by 2. That is 56 by 2 plus 0, that's 28. And similarly, I would say radius equals to sigma x minus sigma y by 2. I would say 56 minus 0 by 2 whole square plus tau square. But I don't know the tau. If I know radius, I could get the value of tau. But I know the one thing also, that sigma 1 equals to c plus r, and center we got sigma 1 as also I know. Then I can say what's the value of radius. So the value of radius, I would say sigma 1 minus center. So the center value, so the radius value would be 70 megapascal minus 28, that is 42 megapascal radius. That's also tau max. So your shear stress maximum would be 42 megapascal. So your radius of 42. So your radius of 42. So let's say this is Mohrs circle. We got this Mohrs circle. Then I would say this one. This is plane B plane on which sigma 2 is acting, and this is plane A on which sigma 1 is acting. That's 70 megapascal. So sigma 2 we don't know, but we want to get this tau xy. This is tau xy, and this is also tau xy. This is also tau xy. Tau xy. So if I am able to get this theta, I can say what's the value of shear stress tau xy. Can I get this? How can we get the location of that theta? We know that this is 180. We know this is 180. Yeah, done. Let's take this element theta. We don't know how can we get this part theta, but one thing is that if we take this triangle, we would say the dimensions would be, this is tau xy. Let's say this is some sigma dash. And I don't know. I know the radius equals 42, but I don't know what's the value of theta. I don't know what is the value of sigma dash. I don't know value of tau xy. But if I analyze the Mohrs circle, I would say, if I know anything out of these three, say from the center, from the origin, we have this part. This is center, and from the origin we have this part that's called as sigma x. That's called as sigma x equals to 56. This is 56, and center, we know that center value was 26. So your center was 26. There 28. I have 28. I have sigma x. That means difference of 2 is sigma dash. Yeah. So if I say what is the value of tau xy, I would say let's say that sine theta equals to tau xy by 42. But I don't know the value of theta. But one thing is that I know cos theta, that is sigma dash by 42. So sigma dash, I know that difference of 2 for 56 minus 28. 56 minus 28 by 42. That means your theta value equals to that 2. We can say 2 theta. This is also principal. This is principal value. From this one, if it is anti-clockwise, I would say it's my negative theta. But for the time being, I would say this is positive value. Some theta, we got some value theta. That's anti-clockwise. It is not of that worry that it's anti-clockwise, no problem. This clockwise, no problem. But we had some theta, we got 2 theta. I would say this is 2 theta. Let's say this is 2 theta. 2 theta p. So I could write this is 2 theta p. This is 2 theta p. I would say sine 2 theta p, cos 2 theta p, and we get 2 theta p equals to 48.2 degrees clockwise. Now you substitute here in this one, and I can get the shear stress value equals to 42 sine 2 theta p. And your shear stress value equals to 31.3 megapascal. So firstly, if you have solved it by directly through the radius, it was very easy. So you had provided that sigma 1 is maximum stress about 70 megapascal, sigma x is 56, and there is some shear stress on that plane. Get the value of that shear stress. So I would say sigma 1 is 60. That equals to sigma x plus sigma y by 2 plus some sigma x minus sigma y by 2 whole square plus tau square. So if I know that 70 equals to sigma x plus sigma y would be 70 plus 0, because sigma x plus sigma y by 2. That sigma x was equals to 56, sigma y was 0 divided by 2 plus, then we know radius sigma x was 56, sigma y was 0 divided by 2 whole square plus tau. Then you can directly get the value of tau xy. But if you solve by Morse circle, you need a lot of that calculation also. That to solve that problem, you need to draw a circle, you need to get this triangle, and you need to get theta, then you need to get tau xy. So this is and all the problems from stress transformation and Morse circle. For the next lecture, would be dealing on strain transformation, strain transformation. So that's the end of this class. Thank you for watching this lecture.